Hi everyone, I'm Rahul and me and TJ, we are going to talk about horizontal scaling support in XLA GPU. So I will start with an introduction to what horizontal scaling means and just give you a high-level overview of the compiler as it pertains to horizontal scaling. Then I will touch on some of the key HLO level transformations or support for horizontal scaling. So that's primly partitioning and some HLO optimizations. After that, TJ will take over and talk about some of the scheduling and low-level optimizations for improving the performance of horizontal scaling, and then talk about some performance results that we have obtained over the last few quarters and then some future work. So horizontal scaling in general is just compiler support to be able to run machine learning models on multiple GPUs. And the reason you might want to do it, I think a lot of talks before have covered that. So you might want to partition your input data and train in parallel, or you might have models that don't fit on a single GPU and you want to shard the weights and distribute them across devices. So there are different kind of model parallelization strategies. And including pipelining, where essentially different layers of the model are placed on different devices. So XLA GPU's support for model partitioning is essentially based around split partitioning, and that's a form of sort of tensor parallelism. What that means is that every operation in your model will be split across multiple devices based on how its output is sharded. And the idea is that the user provides the sharding hints, but then the compiler does the actual partitioning and inserting any communication operations that are required. And ultimately, for XLA GPU, these communication operations are implemented using NVIDIA's Nickel library. So let's look at a high-level flow of the compiler again, just pertaining to horizontal scaling. So what is the input is unpartitioned HLO. So think of it as HLO with large tensors which will not fit on a single device, and these sharding annotations on some key tensors in the HLO. So the first step within the compiler is primary partitioning, where essentially each operator within HLO is rewritten so that it produces just a part of the output tensor as opposed to the complete tensor. And then as a part of this process, the partitioning pass is going to insert these collective communication operations to exchange data between devices as required. So at this point, the job of the compiler, again, as it pertains to horizontal scaling, XLA GPU does a really good job of optimizing the compute part of the graph. So when it comes to horizontal scaling, really the focus is on improving and optimizing collectives. And the compiler sort of employs three broad strategies for that. One is to try to reduce the amount of communication that is required. The second is to reduce the latency of these collectives. So generally, these collectives talk to other devices over NVLink or over network, so they are high latency operations. So if you can try to do something to reduce their latency, that will help. And the third thing is to try to hide their latency by overlapping collectives with independent compute. So in this pipeline, essentially, I'm just going to touch briefly on some of the collective optimizations that we have implemented that sort of target one of these optimization criteria. And then TJ is going to talk about the scheduling related optimizations later on. But ultimately, so we go through a bunch of HLO transformations, scheduling, and we use NVIDIA's Nickel library at runtime to execute these collectives, and the compute is executed through different means. There we have various ways of doing compute. So first, let's talk at a very high level what SPIMD partitioning is. Again, this has been covered in some earlier talks as well. But essentially, you have your model code with written assuming you're running on a single device, and a few key tensors in the model are annotated with the sharding annotations. Generally, the input and the output tensors. So the first step within the compiler is essentially to infer the sharding of all the tensors within the model. So this step is called sharding propagation, and it's an iterative forward and backward pass where you can infer the sharding of the output based on the input or the sharding of the input based on the output. So this pass runs these two phases iteratively till fixed point, and that's how we. So at this point, basically every tensor in your HLO has sharding associated with it. And then the next step is the actual partitioning, where essentially the graph is rewritten so that each operator just produces a part of the output tensor as opposed to the entire one. And As you can imagine, there are cases where we need to get data from other devices, and the partitioning pass will insert these collective communication operations. So these are operations like all reduce, all gather, reduce, scatter, things like that. The sharding itself is quite general. You can express tensors which are fully replicated. So for small tensors, you may not want to partition them at all, or tensors that are fully tiled or even partially tiled. Different JAX APIs like PJIT allow you to sort of construct these shardings using their API level mesh and constructs like that. So after that, I'm going to talk briefly on some of the HLO optimizations that we have implemented. So the first category is optimizations that reduce the amount of communication required. A very simple one is that if you're already using a bunch of tensors and then adding them, you can just add them locally first and then do a single all reduce. So that comes up in some models. I guess the more interesting one is basically the similar optimization but applied across loop iterations. So essentially, instead of doing an all reduce every iteration of the loop, we can just do a local reduction first and then do a reduction across devices outside the while loop. So optimizations around while loops are important because we have been focusing on improving the training performance for LLMs, and a lot of LLMs are sort of expressed as a loop over a layer of transformer. So so a lot of these optimizations for loops are important in that case. So the second category of optimizations is to improve latency. So as I said, so collectives are generally high latency operations, and whatever we can do to reduce the latency should be helpful. So one HLO level optimization here is essentially collective combiner, which is essentially horizontal fusion for collectives. So if you have a bunch of independent collectives and if you sort of execute them natively using Nickel, basically Nickel is going to launch a kernel for each of these collectives, and you have to pay the kernel launch overhead for each of the collectives separately. Instead, Nickel has this group API feature where basically you can issue a bunch of Nickel calls within Nickel group, and what Nickel is going to do is launch a single kernel that implements all these collectives. So what that means is that the fixed overheads like kernel launch overhead are amortized across these collectives. The other observation is that to a certain extent, the larger the size of the collective, the better it is at utilizing the network. So basically, both of these things help reduce the latency of collectives. This is the HLO level example of how this looks. Essentially, today we choose to represent these fused collectives as essentially multi-operand collectives. That works well for today, but it has its representational limits, and we are thinking whether we should generalize it to just a regular fusion, just like how other compute is represented. Okay. Okay, I think that's my part. So I will let PJ take over. Yeah.
So there's another optimization we'd like to talk about. Due to the repetitive nature of LMs, a lot of the transformer layers are implemented in the form of while loops. XLA is not able to schedule instructions across computation units. So if we have collectives towards the end of while loop iteration, as shown on the in the code snippet on the left, XLA is going to have a hard time finding compute kernels to overlap with these collectives. So we introduced this pass, pipelining pass. At high level, it tries to interleave loop iterations. So in details, it peels out the compute instructions from the first loop iteration, put them in a parent computation, and then and the while loop will start from the second iteration. By doing this, we effectively push the collectives at the end of the previous iteration to the beginning of the next iteration. So it's going to have more independent compute kernels to overlap with. Of course, at the end, we need to do a reduce to get the final correct result. So with all these optimizations on HLO graphs, another key piece is a scheduler that's aware of, that's going to produce an optimal schedule based on this optimized graph. We introduced latency hiding scheduler. The motivation behind it is very simple. It's not very efficient to run, to serialize collectives and compute. So we want to run as many of them as possible. And we also want to keep everybody busy on the GPU, including all the compute and communication resources, to have a much better execution plan. So what it is it tries to schedule in concurrency of compute and the collective kernels. It's also able to recognize the async form of the collectives, and also has a pluggable resource and cost model to drive its decisions. So it's a high-level flow chart of what latency hiding scheduler does. So on the left of the chart, we have the default schedule, which originally already use op and then some math kernels. After latency hiding scheduler, you would move some of the math kernels between the start and done ops to for overlapping. Of course, when you run operations in parallel, it has to incur some little bit extra memory footprint. And based on resource availability on the GPU, there will be also a limiting factor for how many collectives we can run in parallel. By default, XLA runs all kernels in a single default stream. So we have created separate CUDA streams to run just dedicated in running those collectives in parallel to all the compute kernels. Yeah, so I mentioned earlier, the scheduler needs a cost model to drive its decisions. The default cost model in XLA wasn't very good. It had 3 levels for latency costs, low, medium, high, and all collectives are assumed to have the highest latency, and then it tries to stuff other compute ops in between based on these 3 categories. Of course, it's very coarse. It didn't do a good job. So we introduced 2 more cost models. The first one is the profile guided cost model. This is by far the closest to the ground truth of the actual runtime of the kernel. So the workflow is we do a profiling run at first, and then get the exact cost for each kernel and dump them into a file. And the file will be ingested back into the compiler in the second run. And then the scheduler will take all the concrete costs and produce the optimal schedule. Currently this flow involves a lot of manual work still, so it needs a lot of polishing. Another model is the analytical cost model. It's reusing the existing infrastructure in XLA to estimate runtime for compute ops, and then we added the estimation logic for collective on top. This is a work in progress. We have set up the existing we have set up the infrastructure to do this. We also have some estimation logic to support single node data parallelisms. And we have also done a lot of low-level optimizations, specifically targeting NVIDIA platform. We need GPU to execute the kernel in the exact same order we define in the schedule. So we have changed the stream executor API in XLA to take priority as input, and we assign the highest priority to all the async streams, so that we want to start a communication as early as possible. And depending on the compute capability, CUDA will create multiple CUDA command queues to launch kernels. So by doing this, it's possible that it's going to launch kernels out of order, and that's not what we want. So this CUDA device max connection is to tell CUDA to only use one command queue for that. So we also, per stream communicators. This is to reduce some of the NICO synchronization costs. When you try to use a single NICO communicator, between multiple streams, NICO will do synchronization at some point. So we create per stream communicator and cache them on the system. Of course, we've done some work to eliminate some CPU-side rendezvous overhead before launching collectives. And also, we have done tuning of NICO environment variables to get the best performance. NICO supports low latency algorithms, which are very efficient on systems with the direct GPU communication. So these are the environment variables we use to enforce NICO to use the low latency protocols. So some performance numbers. Of course, there's a very close collaboration between NVIDIA and Google, and performance has improved by 2.5x on Ampere. We also observe nearly linear scaling to up to 1K GPUs. A highlight is when doing FSDP style partitioning, the scaling efficiency improved from 91% to 99% by combining all these optimizations we talked about. Also, there have been a lot of optimization and custom kernels fusions introduced into XLA. So by combining the scheduler work with all these kernels, we observe further speedups. And some future work, we are optimizing collective permute to improve the performance for pipeline parallelism. Also, the ongoing work to improve the analytical cost model. We're also improving the user experience for the profile-guided one. Collective combiner improvements, that's another important path. We want to fuse as many collectives as possible, so we're trying to generalize the logic there. We're also doing experiments and trying to see the experiments with different phase orderings with respect to scheduling, hoping to produce more optimal schedule. Collective matmul is another important optimization. We partition large matmuls into smaller ones and then inject collectives and also efficiently hide collectives between each of these partitioned gems to reduce peak memory. Also, we are actively looking to reduce the host side overhead even further. So for Grasshopper platform, because of the high bandwidth interconnect between GPU and CPU, we can do much more efficient offloading of activations. So there's another optimization down the line. Without these, I think, yeah, that's a wrap. Questions?
Yep, Sudipta from AWS. Good to see use of XLA in the GPU stack. My question was, how can customers use it today? Is it going back to the open source for GPU backend for XLA, or is it coming in NVIDIA product?
Oh, well, no, everything is in the open XLA GitHub repo. So yeah, there are some flags, I mean, to enable different optimizations. Some of them are turned off by default, but everything is documented in the repo.
And is the work specific to JAX today, or also work with PyTorch XLA?
It's mostly done for JAX. Yeah, we haven't.
The work itself should extend to PyTorch XLA. It's just that we haven't experimented with PyTorch XLA GPU integration yet.
Got it. Thank you.
Hey, you talked about multiple asynchronous streams during computation for the kernels. TensorFlow uses XLA as one of its backend, right? And TensorFlow talks about having a single compute stream. So how are you envisioning it when you engage it with TensorFlow?
Yeah, I would delegate to you.
Yeah, I mean, we haven't done horizontal scaling integration with TensorFlow that much yet, but like what we have right now is still a single compute stream for compute and another stream for collectives. And if you think of TensorFlow as executing XLA executables, there is still synchronization at the start and the end. So everything is synchronized with the main stream. So as long as that continues to work, which like within XLA, we should be able to spawn as many streams as long as they all synchronize at that.
Just to follow up, is there a limit on the number of streams that you're planning to spawn?
I mean, there's no limit on the CUDA side. It all depends upon what gives us good performance. For example, we have considered but not implemented potentially having multiple streams for collectives. So let's say you have a local collective which is going to use NVLink, and you have another collective which is only going to talk across hosts. Potentially, they could be done concurrently. Now we need to see if that actually happens in models and is it useful. Similarly, for compute as well, we have considered having multiple streams for, independent kernels. The question is, is that the best strategy? Or, I mean, XLA also supports horizontal fusion for, basically you can combine independent kernels. Maybe there's an advantage in doing that, sort of better predictability of the schedule as compared to multiple streams. But yeah, I mean, those things are on the table. Yes.
Thank you.